The continents are not granite, though. The continental average is something in between, but we don't actually know it very well, Chris. And this is why, I mean, I love this stuff when it's like a fundamental thing that we don't understand as a scientific discipline. Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
Yeah, let's do it, Jesse. Okay. I'm just gonna say right from the outset, I have a massive head cold, and so
there's a frog in Chris's throat. It's croaking away too.
It is. So I will definitely crack during this episode. So I apologize in advance.
You'll have the old teenager squeaky voice cracks every once in a while, won't you?
You know, Jesse. It's when I get excited and I start to talk a lot. That's when it cracks the most, and it goes. So I got to try to stay calm today.
That's very funny. Staying calm might be tough on this topic here.
I know it is tough.
This is part one of probably a couple. And we're talking about, we're on my home turf again, Chris. I feel sorry for you and for the listener here. But we're talking about the continental crust. What is continents? How do we make it? You had a good catchphrase in the intro. What was it? How to make a continent? Is that what you said? Is that how you, or how to
stabilize a continent?
How to stabilize a continent. Right? Yeah, exactly.
Yeah.
Oh,
right. Well, you've alluded to this a number of times, and we never really dove into it. And the other thing, Jesse, is that what we're gonna talk about today, to some extent, is gonna contradict what most people know about the composition of the crust of like continental crust.
Yeah, that's sort of intro,
especially at a rudimentary level, at an intro level.
Yeah,
physical geology class. What you've learned is wrong.
So, what do you mean by that? What do you learn at an intro level class about the continental crust? That's wrong.
Okay, I'll be the first to say that I'm guilty of this.
Oh yeah, we all are.
Yeah, for sure, and I think we have to be, and I think it's okay. But continental crust is felsic, and so we say that the continental crust is granitic, and that's the part that's not entirely true. It's only partly true.
It's only partly true. That's right. And if we look at the rocks, we've talked about this before. We look at the rocks on continents. What we see a lot of basalt. We see a lot of granite. And there's reasons for that. Granite is sticky magma that kind of sticks beneath the surface. It does not erupt as much. And when it does erupt, it erupts in huge volcanic eruptions. Basalt is much more runny. It can make its way to the surface. So we see those two rock types very commonly. But we see also sediments. Sediments are very felsic in our terminology here. They're very rich in silica, aluminum. They have less magnesium, less iron in them. And so the sediments are also felsic in our minds. We're going to put felsic and in one category, which is granite, sediments, etc. We're going to put mafic in another category, which is basalts. These are gabbros. This is oceanic crust typically. But the average of those two things is not felsic. The average of those is somewhere in the middle, is intermediate. And we often think of like granite as really felsic. The continents are not granite, though. The continental average is something in between, but we don't actually know it very well, Chris. And this is why, I mean, I love this stuff when it's like a fundamental thing that we don't understand as a scientific discipline. I love that type of stuff, and it makes you a little uncomfortable sometimes about that. But how does this one make you uncomfortable?
Well, just a little bit. I'm getting better with it, and we've talked about this before. I get a little uncomfortable when I don't like to say that we don't know. It bothers me, and that's what we really don't know. So Jesse, the deepest borehole is this Kola borehole that the Russians drilled down 12.2 kilometers. That's as deep as we've actually been able to directly get to, which is sad. Yeah. It's so sad when you think about, in relation, it's a major accomplishment, don't get me wrong, but when you think about the thickness of the crust, 35 to 75 and even thicker if you're talking about mountainous areas with deep roots, 12.2 kilometers is it.
It's not very much. That's right. We haven't even,
it's not very much.
We haven't even gotten into the bottom of the upper crust at that point, the upper continental crust. So all these models for continental crust, you said, Well, okay. You said 35 to 75, I think is what you said, which is 75 is kind of, or 70 is really the thickest that we see of the continental crust, the crustal thickness. So the surface of the earth to the moho, that range. The average is probably closer to 35, a lot closer to 35. It's somewhere in that 35 to 40 range. But Chris, this episode's going to be full of a lot of little thought exercises, I think, because it's an important way to think about this and I think to kind of plug into the science of it. So listeners should try and go through these thought exercises as we're talking about them. Like, think about the question. Our drill holes have only gone down to 12 kilometers when we're talking about 35 kilometers on average thickness of crust. How would we measure? How would we get information about the middle and the lower crust, or the lower crust, the total package? Some people divide it into three, think about the continental crust divided into 3 layers. Some think about it divided into 2 layers. How would we get information about those bottom 1 or 2 layers? Like, where would you go on Earth? What rocks would you try and pick up to find that stuff? Or what geophysical techniques would you use to try and understand what is going on down beneath our feet? It's a really interesting problem, a really interesting question to ask. And what do you think the average student of yours would say to this? Because I've never done this exercise. I've never asked intro level students this question. It's a very common question in like the PhD qualifying exam or the candidacy exam committee. Like, think about, what do we know about the lower crust? How do we know that? That's a very common thread. But I'm curious what you think the intro level students would say to this.
I don't know. I don't know. I think that my students that are seniors and have gone out west with me and seen the routes to mountain ranges, essentially, maybe would be able to come up with some reasonable hypothesis, I think.
Okay. You think,
but I'm not sure. I don't know, because I've never really asked this either.
Yeah.
And I'm going to start asking this question, because it's a good thought exercise. I mean, you and I have talked, I think, pretty extensively on this in our audio podcast series on the Tetons, or the podcast series on the Grand Canyon. I think that we didn't like directly say this, but we indirectly did, right?
No, that's right.
We talked about minerals that we see, right? In the Vishnu schist, for instance, we talked about these garnets that formed 20 miles beneath the surface of the earth, and here they are now exposed at the surface. And so I think just like walking through, well, how did that happen? Those rocks, they're now at the surface, but they formed moderately deep into the crust. So they give us that glimpse, right?
They give you a glimpse. That's exactly right. And this comes into the question. So you're touching on exhumed terrains is one answer to the question, where would we go to look at the middle to lower crust? And you'd go to places where there was big mountain belts formerly that have been eroded, and the roots of those mountain belts are now exposed on the surface. And there's a bunch of locations on Earth. We think of these, especially for the lower crust, the lower part of the continental crust, we call these granulite facies. That's a metamorphic grade. It's really high temperature, really high pressure. We've covered this in our CampGeo on our app, on the CampGeo app. We talk about metamorphic rocks and metamorphic facies or facies, and granulite is the really high temperature stuff, the stuff that has been melted. So we have rocks on the surface. Southern India has a big granulite terrain. There's a big exposure in the middle of Europe that's called the Variscan, and there's places in the United States that have these lower crustal components. A big block of lower crust that's kind of come up in some way, shape, or form. These metamorphic core complexes are exposed at the surface, usually, as you said, in like former mountain belt collisional areas. So we call those exhumed terrains, and that's lower crust stuff that used to be down at really high pressures that's been thrust up in some way, shape, or form. Okay? And we can walk across those, we can map them, we can look at them. Tons of people do that. Colleagues of mine at Penn State do that a lot, and try and understand their composition, what happened to them, how did they melt, etc. What do you think?
And this is just this, I was just going to say that this is that really rinse and repeat process of, you have this uplift, and then you have gigantic belt grinder from above, weather and erosion, stripping rocks away, removing mass, bringing it down to the valleys. It gets mass wasted away, and then more uplift. And so you just gradually bringing these deep-seated rocks to the surface. Right.
Chris,
Jesse, one thing.
Yeah, go ahead.
One thing that I do ask my classes, though, is, all right, well, we've talked about how granite forms. The classical idea of what a magma chamber looks like and its slow, relentless cooling. Well, okay, well then if that's it, this is really, really deep-seated stuff, then how does it make its way to the surface? Why is granite such a common rock at the surface? So I do ask them that. And it's an interesting thing because most of them never really thought about it. Wait a minute, you're right. Wait, why? How is that so common?
Yeah.
It's really this process, just not as extreme.
That's right. So basically what we can see when we look at these exhumed terrains, they have a fair amount of felsic material in them. So these are a lot of sediments that have been shoved down by tectonic processes, shoved down into the deep crust, have been metamorphosed. They've usually been melted, and melting is distillation. And so they've usually been partially melted, and then at some level they've been tectonically brought back up. So the residual stuff, the stuff that was left behind after melting, has been brought back up to the surface, and we can look at that stuff and see that it has lost.
And each time this happens.
And each time that happens, but in a tectonic...
That's right. And each time this happens, it gets more and more felsic, right?
It gets more and more felsic. However, it's kind of locked by granite. Like, you can't get more felsic than granite just because of the thermodynamics of the system. And this is a really important part. So the upper part of the continental crust, we think we have that kind of nailed, the composition. This upper 10, 15 kilometers is a lot of sediment. There's a lot of granite. It is granitic in composition, that upper part. And we have really good estimates of the even down to sort of the uranium and thorium concentration on average of the upper part of the continental crust. It's when we start to get lower and talk about the bulk continental crust is that we don't really know too much about that. Or we have some estimates, but there's not much agreement on the composition of that. So another place, Chris, which is less intuitive than these exhumed terrains, another place where we could go and pick up a rock and say, ooh, this came from the lower crust. Do you think students would get to this? Like, hey, this is an area the Xenoliths could record this record, or no? It depends if you've talked about diamonds first or not. I think like if we've talked about diamonds and how they get out.
No, I definitely have not. Yeah, I definitely have not. Diamonds is going to be a conversation that just comes up because it's an organic conversation. They want to know, they'll ask a question about diamonds and then, okay, well, here we go. We're talking about kimberlites and, we're going to talk about these pipes that come up from deep, deep down. But there is a way that they can maybe arrive at this, and that would be through their knowledge of a porphyritic igneous rock, like a porphyritic andesite or something like that, right? Which isn't this, but it's close.
Yeah, okay. In what way? What do you mean by that?
Xenoliths, we think of that as the chunks of rock, country rock that get broken off and not really consumed, in the magma that is bringing this kind of slush up to the surface. Porphyritic rocks, it's similar to that in that you have these, a deeper seated magma chamber. You have these early formed crystals, and then when the volcano erupts, it brings those slushy crystals with it to the surface. So they're coming from deeper down. Does that make sense?
Yeah. No, that's exactly right. Yeah, they're coming from deeper down. In this case, they're coming from far deeper down. So we can go to places like the Basin and Range, for instance, where there's all this extension. The continental crust has been thinned. It's been cut in half it's been stretched twice. So, twice as long. So it's half as thick. And there's basalt erupting through there. It's a mantle melt. It's forming at the base of the continental crust, and it's erupting through the continental crust. And sometimes the stuff that it picks up at the bottom, in the middle, in the top, is carried up with the basaltic lava. We find these as xenoliths. So we can look at these and measure these things. And people have done this for a very long time. There's a bunch of people who've spent a long time categorizing this and trying to answer this question of what is the continental crust. And they looked at the xenolith record. So these are little pieces of the lower crust, middle crust, that have been carried up in lavas. And if we look at those, they have a broadly mafic composition or a dominantly mafic composition. Those things are very heavily weighted towards basaltic. They're metamorphosed basalt at granulite facies conditions. So you take a basalt and you metamorphose it to really high pressures and temperatures, 700, 800 degrees centigrade and 30, 40 kilometers thick, 40 kilometers deep. That's going to be a granulite facies rock. that's what these things dominantly look like. There's hints of sediment. There's like 10-15% sediment in the Xenolith record, but it's heavily weighted towards mafic stuff. And so that data is a large reason why people have argued traditionally for a 3-layer crust, a 3-layer cake for the continental crust. We have really felsic stuff up top. You have intermediate stuff in the middle. This is more like andesitic composition stuff in the middle. And then the bottom would be mafic, would be basaltic in composition. That 3-layer approach kind of comes from the Xenolith record.
Okay, that's interesting. I want to come back to that comment in a second. But before we do that, so these are in contrast. Does it maybe mean that the exhumed terrains, through isostic adjustment and this gravitational resetting, if you will, maybe that's not as deep-seated as where these xenoliths come from?
It's a good question. It could be true. However, we do have very deep-seated stuff. We can, and if you take a shale and you metamorphose it, we have all these cool minerals that form. We have garnet, we have kyanite, we have slumonite, all these really cool minerals that form that give us a pretty accurate pressure temperature data point. So we can say, oh, this mineral grew at really high pressures. And so we know really with a good deal of confidence that some of these sediments were down in the lower crust at least. But I think you're bringing up a really important question, which is, okay, we've got this exhumed terrain thing, we've got xenoliths. Are either of those...
They appear to contrast each other.
Yeah, they're kind of different. And to the exhumed terrains kind of have a similar composition broadly to the continental crust. There's like a big peak in the mafic category, and there's a big peak in the felsic category. So like a big population of them that's mafic, and then a big population of them that is kind of granitic and sedimentary. So you get kind of this bimodal, 2 modes, two groups in the compositions here. In the terrains, in the exhumed terrains. And the question we have to ask is like, are either of these, one or the other of these, biased in any way, shape, or form to kind of preferentially give us a view of maybe too felsic or maybe too mafic when we're thinking about what gets brought up to the surface? And is our surface exposure, we know rocks in the surface are biased compared to what's down at depth, but how much is kind of the question here.
It's an interesting thing, Jesse, because andesite's missing from both of these.
Right.
And if we had a 3-layered cake, that wouldn't be the case. I mean, that's not to say that we don't have andesite in the continental crust, but it's a niche setting. This is the subduction zone related partial melting, this kind of tectonic, very specific setting where you get andesite, but we don't see it in either one of these situations. We don't see xenoliths that are bringing up andesite. We don't see exhumed terrains that have enough andesite to really speak of either. So it's an anomaly to me.
That's right. It is. And that kind of alludes to a third category where there are a few locations on Earth. They're more recent, they're more modern settings, but there are places where an entire section, an entire subduction zone system has been tilted on edge, and we get a window going from the upper crust all the way down into the lower crust of a former arc. And so the Sierra Nevadas have this. If you go from Tuolumne, if you go from Yosemite National Park and you head south, you basically get down into the roots of a volcanic arc, deep down into the roots. There's a famous one called the Kohstan Arc batholith. It's kind of caught up in the Himalaya collision there, and it's another one of these that's been kind of tilted on edge. There's one up in Alaska, Talkeetna. And so there are arc terrains where we can get this like cross section through a continental arc, but that's a relatively modern, well, depends when you believe subduction started on Earth, but that's one particular tectonic setting, and it's not a collisional zone setting. It's exposed and tilted in a collision, but it was formed in a juvenile arc setting. So it's not necessarily totally representative of the continental crust necessarily. In all these terrains, let's go back to the Xenolith one. They could all be biased, or they almost certainly are biased in some way, shape, or form. So exhumed terrains, well, maybe sediments are more likely to get exhumed. Like that would make sense. They're a little bit more buoyant. Maybe in a big continent collision, you smash stuff together, you erode off the top of the huge mountain belt that's formed, and everything doesn't rise back up to the surface. It's kind of like we use this cargo ship analogy a lot when we're talking about this process, Chris. Like,
it's a good analogy.
It's a great analogy. The cargo ship, you start to unload the top layer, and the whole rest of the ship kind of rises up, right? It floats higher. And so by the time you're getting to the bottom layer of the cargo, that stuff is riding a lot higher than it used to. But that's not actually how it works. So you don't just unload all the layers all at once. There's more of a feedback loop. Like, you could unload one side, it starts to float a little higher, which on Earth, that would mean that it makes it easier to erode that because it's a little bit higher. So then there's feedback loops in how this stuff erodes. So, and if the lower part is more buoyant and the ships are already tilted to begin with, a fully loaded ship has all the light stuff up front, all the heavy stuff in the back, it's a little bit more tilted, you might start to erode the stuff in the front quicker, which means the front nose would float higher quicker. If that makes sense? Like,
yeah, it does. Yeah.
So
sure.
that's the way to kind of think about it.
Let's ask the question then about the xenoliths then, and why they are predominantly more mafic. And just, this is again another maybe thought experiment. Well, how might that be biased? Could there be felsic xenoliths that were there on the way up?
Right. Well,
right?
What happens, Chris? What happens when you take a 1200 degrees centigrade basaltic melt and you flush it through a bunch of sediment? What happens to that sediment?
You melt it.
It's going to be assimilated, right? So
yeah.
So maybe there was a whole bunch
because of lower temperatures,
lower melting temperatures,
yep.
exactly.
Lower melting points.
Yeah.
Yep,
so
absolutely. Felsic minerals have low melting points.
You could totally melt the granite into the basalt and lose that xenolith record, and only the mafic stuff survives, right? In a way, we often see this process in reverse. We see really low temperature granites with mafic xenoliths in them because the low temperature felsic granite does not have the thermal power to actually melt the mafic xenolith that's intruded in it. But you do that in reverse, and the basalt has a lot of energy and can melt that thing. So that's one example of a way that this record could be potentially biased. And so all of these are potentially biased. You know, the subduction zone, the tilted subduction zone sections, those could be biased towards a tectonic setting. They could be just only giving us a view of a modern subduction zone system, or relatively modern 100 million year old subduction zone system, which is not necessarily indicative of how the entire continental crust formed over 3 or 4 billion years. So we're kind of at a conundrum. I mean, I think there's not a ton of agreement on this 3-layer 2 model. So if I just come back to this 3-layer 2-layer model, basically there's two camps. Like, there's a couple different models for a 3-layer model. It's felsic up top. Middle crust is from 12 kilometers to 25 kilometers is intermediate. And then from 25 kilometers to 35 or 40 kilometers is mafic. That's kind of the one model. The other model, the 2-layer model, says the upper crust is felsic for sure. It's really granitic, almost close to very granitic up top. And then the lower crust is intermediate. And that is their model. So from 15 to sort of 40 or 35 kilometers is intermediate. Then it's a 2-layer model, and we'll come back to that theme later on, which is what happened to the bottom layer, I guess, in that model. But I don't know. It's an interesting thing. Like, one of these things in graduate school for me, where you sort of realize, wait, we don't understand a lot about the Earth. We don't understand when continents formed. We don't understand actually what the composition of the continents are underneath of our feet. What is the average continental crust? It's interesting that we don't know that very well. I mean, we have some pretty good estimates, but we don't have it nailed, which is interesting.
So what do you subscribe to? 3-layer model or 2-layer model?
I'm not really sure. That's a tough question. I think the 2-layer only because it's a little bit simpler.
Yeah, but it's not just that though, Jesse. You have a lack of diorite and intermediate rocks. They're just not that common.
Right. Yeah, that's right. And I think it goes.
I would.
What do you? What's the crystal ice?
Yeah, I agree. I agree with you.
The 2-layer, just because it's
2. My gut is just because, like, it's just, to me, I cannot get my mind past the lack of those types of intermediate rocks at the surface. I just think that we would have more of it. But I don't know. I mean, we don't know, which leads us to the next segment here, Jesse, is, why do we care? Why are we talking about this? Why is this important?
There's a lot we don't know about the Earth, but why do we care, right?
Yeah, right. It did get me thinking, though, that Jesse, you threw out some words that are near and dear to my heart, places that you and I could have a lot of fun walking through Tuolumne,
absolutely.
going to Cathedral Lakes and up by Clouds Rest and just, hiking through the heart of
thinking about
Yosemite.
The composition of the continental crust. I mean, what more could you want in a vacation? I mean, my goodness. So why do we care what the composition of the continental crust is? Well, the composition tells us a lot. It tells us how it formed, really. It tells us the process by which it formed, because we know that different igneous rocks, different compositions of igneous rocks form in different ways. The granites or the rhyolites that are erupted on Iceland are incredibly different from the granites and rhyolites that are erupted in Yellowstone, or the ones that are erupted on any subduction zone system on Earth. And so that tells us a lot. If the average continental crust looks like a subduction zone system, or looks like Yellowstone, or looks like Iceland, it tells us that maybe that's how the continental crust actually formed. The process by which the continental crust got stabilized. How do you build a stable continent? So the composition matters a lot. And I think if we wanted average composition of the continental crust, if there's one rock type, Chris, this is a little quiz. If you could measure the geochemical composition of one rock type to estimate the average of the continental crust, what would you look at?
Of continental crust? Or just the composition of the Earth?
Composition of the continental crust. Well, two-parter. Okay, what the composition of the Earth first, and then composition of the continental crust two.
Well, I think for the composition of the Earth, I would want to know the composition of meteorites.
Okay, good. Non-intuitive, though. Why? Why meteorites?
Because that's going to tell us what the interior of the Earth is. That we definitely can't see. We're never going to get to see
the building blocks of Earth, right? Yeah, exactly.
Right.
So okay, right. Okay, great.
Now that's easier, I think, than the other question.
Yeah.
This is seriously. So what you're asking me? I want to be straight on this because we didn't talk about this. So
no, this is impromptu quiz, Chris time.
I know. You want to know what rock I would want to know a geochemical analysis of to help me understand the chemical composition of the crust.
And the upper crust, let's say.
The upper crust.
Which is kind of a hint.
Oh. Well, I would say granite.
Ooh, okay. Why granite?
Because that's primarily, I don't know. I mean, we do have a lot of sedimentary rocks in the upper crust too, but
closer, warmer. Warmer. What is it? What sediment best represents the average continental crust? If you could take a big ass sample,
a big ass sample of it,
yeah.
Shale.
Shale is the classic one. Shale. If you had a big sample of shale, people have used this as like average continental crust in some way. Sure. There's one that's more recent. People have been focusing on, which is diamictite, which is take a huge sample of glacial till and go back in time and say, oh, there's old diamictites, there's old till samples. A till is just glacial kitty litter, as you describe it. That's a pretty good estimate for average because it's just unsorted. There's big boulders in there. There's little fine-grained clay particles, and people have looked at diamictite back in time.
I don't feel that's a fair. Okay, that's not fair.
I didn't say it was fair. But shale, you got it right. Shale is the one that people have used for a long time as a good estimate for upper continental crust composition. And it turns out that composition looks, in major elements, in trace elements, it looks kind of like a subduction zone system. We have a depletion in the elements that subduction zone magmas are depleted in. There's enrichments in the fluid mobile ones that subduction zone systems are enriched in. We have more uranium than thorium. We have all these signatures that look kind of like an arc system that are preserved in the upper continental crust. And so that's just one indication of like why the composition matters, because it tells us something about the formation processes of the bulk of the continental crust. That subduction or processes like subduction were probably important for the majority of the continental crust, of construction of the majority of the continental crust. So
But that does present a problem, though, because when I think about a geochemical analysis of a rock, I don't just want to know the elements that are present there. And to me, then shale makes sense because, the most common mineral at the surface is feldspar, and feldspar chemically breaks down into clay, and clay is what makes up shale and so on. That makes sense. But what you don't get out of that is a timestamp, really, or at least a good timestamp. We need to know age as well.
That's right.
And that's a problem. Igneous rocks are more straightforward for that.
Yeah. That is a great.
That's why I was torn.
That is a great comment, Chris. I'm very happy you said that because I think that leads.
I bet you are.
I think that leads. We don't. I use a slide when I introduce a bunch of talks about early Earth stuff, and everybody else who gives talks on the early Earth use a very similar slide, and the slide shows the range of models that people have proposed for when continents grew on Earth. And basically some people argue that we had the exact same volume of continental crust that we have today 4.2 billion years ago. And some people argue we only had 50% of the continental crust 1.5 billion years ago. There's a huge range.
Oh my gosh, that's such a
and like
that's ridiculous.
Basically you look at this plot and the entire area of the plot is filled with model lines. Like we just don't know. And so your point is exactly that. Even if we know the composition of the continental crust, it doesn't tell us much about time. And there are blunt instruments we can use to understand the bulk composition of the continental crust. So there are these things called model ages, like the meteorite record. We know when we look at meteorites, we can look at those and we can measure the neodymium isotope composition, which is a samarium neodymium radioactive decay system. We can measure the lead isotope composition, which we've talked about before. Uranium decays to lead. There's 2 isotopes. There's a bunch of different isotopic systems that are constantly decaying away. And what that means is the isotopic composition of, let's say, neodymium or lead in a bulk meteorite will be changing over time because of radioactive decay. So 2 billion years ago, there was less radiogenic lead than there is today. So we can do the exact same thing based on a model of Earth. We can measure average neodymium isotope composition of continental crust or shales, let's say, or diamictites. We can measure the lead isotope composition of those rocks. And we can say, what's the average age? And we say average age, we use this as like a depleted mantle model age is the technical term, but we don't need to get into the weeds of that. It's just a rough estimate of the age. It doesn't tell us when the rock formed. It tells us when the mass of the rock was extracted from the mantle on average. It sounds really vague, and it is really vague, but it's all we have. So when we do that for rocks like shale or diamictites, the average age of the time of extraction of the continental crust is 2 billion years, around about 1.9, maybe 2.1 or something like that.
Oh,
average of about
okay,
2.
That's interesting. Okay, I would have thought older.
Okay,
because you're relying upon the date of when those minerals formed, not when the rock was laid down.
That's right.
Which are 2 really, really different
totally
things.
Different things. You're right.
I would have thought it would have been an older age.
Okay.
So what you're suggesting then is continents are younger.
Well, it's a good question. The average extraction of the mass of the continents from the mantle was around 2 billion years. But does that mean that continents were formed 2 billion years ago? No, definitely doesn't mean that. Because 2 billion years is around about the age of the Earth. Half the age of the Earth, actually. So is it just
less
2 billion years?
Yeah.
Let me correct that.
You threw me for a loop there. I thought we were changing. I thought we were
we're revising the age of the Earth here. Yeah, didn't you know this, Chris?
Hey, it's our podcast. We can do what we want.
With the age of the Earth is 2 billion years. No, sorry, I misspoke there. The 2 billion years is round about half the age of the Earth, which means it could just be an average. It could be continents started forming 4 billion years ago, progressively grew till 0, and the average is 2. So we don't really know how to interpret that. We know that it's not 4 and it's not 0, right? But it's somewhere in the middle, and like I said, it's a really blunt instrument. But I think that might be a place where we want to leave this episode, Chris, and come back to that, because how continents get reworked and overprinted and recycled is a really complicated question. And again, like I said before, there's very little clarity or very little agreement on this topic in the scientific literature on when continents grew. And there's some nuance into that. I think it's an interesting discussion, like what the various arguments are.
Oh, for sure. This is great mental gymnastics for me.
It is. It's fun to think about. I'm not sure how easy it is to make progress because it's a really intractable, really tough problem. It's a really tough problem.
It is. But I don't feel good about ending right here, though. I feel like we need to, for our listeners, we need to sum up, like, what's the takeaway for today? We've said a lot of we don't know. We don't know how continents really stabilized. We don't know when they really stabilized. There is a lot that we don't know. So what would you say the takeaway is for today's talk?
What have we done? I would say that we don't know a lot, but we do know some things, and we'll come back to the distillation thing. How does it stabilize? We have a good sense of stabilization, perhaps. We'll come back to that. We'll come back to the timing thing. There are models out there. There are ideas out there about when continents formed. I would say that the takeaway, what do we know? We don't know whether there's 2 layers or 3 layers, but we know that the average upper continental crust has a lot of similarities to a subduction zone system. And so fluids and subduction-like processes maybe were part of the process that formed the bulk of the continental crust. So we kind of know water was involved. I think that's a pretty safe thing to say. And there's this famous paper from 1983 that laid out...
Well, hold on, though, Jesse. Water coming out of the magma, right? This distillation process.
Yeah, water moving elements into the continental crust. And the way that happens on the modern Earth is the oceanic plate. You described it as a sponge that soaks up a bunch of water. When it goes down the subduction zone system, it gets squeezed out. When it gets squeezed out, uranium goes with it, whereas thorium stays behind a little bit. And so we have things like barium that are enriched in the continental crust relative to other elements. So things like that are they kind of indicate that water was involved. And there's this famous paper from 1983 by Campbell and Taylor where the title, this is a great title. The title is No Water, No Granites, No Oceans, No Continents. And the point was that granites require water to be made on Earth. And the continents, the upper continents, have a lot of granite in them. So if we don't have water, then we don't have granites. If we don't have oceans, then we don't have continents. And that was the point that was made there. And I think it's a good one. And I think the data, kind of backs that up, that water and potentially subduction zone processes were kind of instrumental in forming the bulk of the continental crust, at least.
Well, there we have it.
How do you feel about that?
It's good. It's not done.
It's not done.
So this is part 1 of at least 2, maybe part 3. We don't know yet about that, but this is not done. So
that's right.
But I think it's a good spot to end, because then we're going to move into next up is going to be really the stabilization of a continent, reworking it, recycling it. Hence stabilization.
What does stabilization
which is
mean?
Something that you've referred to a ton, and we just never really explained it. And we're going to get into that.
Sounds fun. I can't wait for it. All right. Hey, with that's a wrap. You can follow us on the social medias, Planet Geocast. Send us an email. There's a contact us link at our website, planetgeocast.com. And download the CampGeo mobile app. We talk about this and a bunch of other stuff. Intro to Geosciences there on the app, with a bunch of other audiobooks going to the bottom of the Grand Canyon, right, Chris, where we have some of these sediments exposed that made it to great depth. So check that out. Feel free to send us an email.
Cheers.
Peace.